Hello, welcome everybody, and thank you for joining my presentation today. I am going to talk today about joint work with Abebe, and our paper is titled Fairness, Equality and Power in Algorithmic Decision Making. And so by way of introduction, there has of course been a large debate in recent years, both in the computer science literature and in the wider public, about the fairness of algorithms. And fairness of algorithms usually is understood in these discussions as the absence of discrimination. And what we are trying to do in our paper here is kind of two things. The first one is making a case that most of the leading definitions of fairness have some key normative limitations. And in particular, we argue that they first legitimize inequalities justified by some notion of merit. Second, they tend to be narrowly bracketed, so they only tend to consider differences of treatment within the algorithm rather than differences of welfare-relevant outcomes in the wider population. And third, the majority of definitions tend to focus on between-group differences while ignoring within-group inequalities. And so that's going to lead to some unwelcome evaluations, in particular in settings, for instance, where predictability is increased, that often increases inequality while decreasing unfairness. In settings where affirmative action or compensatory interventions are abolished, that tends to, again, improve fairness but make inequality worse, and similarly for within-group inequalities. And so motivated by these normative limitations, we propose two alternative perspectives on the normative evaluation of algorithms. And the first perspective asks kind of the consequentialist question: what is the causal impact of the introduction or modification of an algorithm on inequality, so on the distribution of welfare-relevant outcomes in the population? And the second question asks kind of, in a way, who's on the other side of the algorithm? Who has the power to actually pick the objective function that the algorithm maximizes? Right. So whereas the first two perspectives just focus on differences between different people who are being treated by an algorithm, this perspective asks who's actually on the other side of the algorithm. And to make things a bit more formal, here's the type of framework we have in mind. So there's some binary treatment, W, that we're interested in. Could also be continuous, but for the sake of specificity, I'm going to focus on the binary case. There is some underlying treatment return on merit, M. So this is usually the type of objective a firm might have, something like profits or related objectives. And then there might be a treatment cost C. And what the decision maker, so again, think of some firm, tries to achieve is maximize this objective mu, which might reflect profits. So mu is equal to the average across units or individuals of W times N minus C. So if somebody is treated, then the firm gets return M and has to pay cost C. If they're not treated, the firm just gets 0. And so in my presentation throughout, all averages are averaging across individuals on expectations. So I'm going to ignore uncertainty or learning for the purposes of this talk. And correspondingly, so M tends to be unobserved for given individuals. So that's the learning problem, predicting M given some observed features X. But suppose we have enough data from some other setting where we can learn the function which maps X into the conditional expectation of M. So I'm going to denote it MX. Then, of course, the optimal policy for the decision maker who cares to maximize mu here would be to use W star X, which is to treat everybody whose predicted merit MX exceeds the cutoff of treatment cost C. And there's all kinds of settings that have been discussed in the fairness literature which kind of fit into this framework. So things like bail setting for defendants based on predicted recidivism. Right, so there W would be whether or not somebody goes to jail, and recidivism would be M, or the screening of job candidates based on predicted performance. So in this case, performance or productivity would be M, and whether or not somebody's hired would be W. And similarly for consumer credit based on predicted repayment, the screening of tenants for housing based on predicted payment risk, or the admission to schools of students based on standardized tests and their predicted future educational performance. And now in this type of setting that I just introduced, there is all kinds of definitions of fairness, of course, that have been proposed. But what we argue is that the majority of them share some key characteristics that might not be desirable. And so in particular, the majority of these definitions combine three ingredients that are already laid out. There is some treatment W that we're interested in. So we're interested in whether or not W is fairly allocated, or W might be whether you get a job or credit, or whether you're incarcerated or admitted to some school. There is some notion of merit M, which is kind of what the decision maker by himself care about. So things like marginal product of workers, or credit default, or recidivism or test performance. And then usually there are some protected categories A, so things like ethnicity or gender or race. And as I said, there are many definitions of fairness based on these ingredients. For the sake of concreteness, let me focus on one of them, which is what's called predictive parity in the machine learning literature. So predictive parity says that the average merit among the treated, so the expectation of M conditional on W equal 1, should be the same across the different protected categories A. So the expectation of M given W equal 1 and A equals 1 should be the same as the expectation of M given W equals 1 and A equals 0. And this is the definition that also has a longer history in economics. So in economics, this is known as the hit rate test for taste-based discrimination. And then there's all kinds of things you could do with this definition. One, for instance, would be to think about machine learning subject to a fairness constraint. So maximizing profit subject to the constraint that pi is equal to 0 here, for instance. That's not what I'm going to do in this talk. Instead, I'm going to argue that this type of definition of fairness has a number of limitations. And so the first thing to note here is, in a way, it's a notion of fairness that's very well aligned actually with profit maximization, and that's no coincidence. So if you assume, for instance, that W and M are binary as in the classification case, and if M were perfectly predictable, so kind of the limit when you have enough features to achieve really good prediction of merit, and if the firm engages in unconstrained profit maximization, then in that case, W star satisfies predictive parity automatically. So in a way, profit maximization and fairness are almost the same thing here. So if a firm is maximizing profits and observes everything, that decisions are fair by assumption. And crucially, that's the case no matter how unequal the resulting outcomes are, either within or between groups. And so almost by definition here, only deviations from profit maximization are considered unfair. And that's, of course, no coincidence. When Gary Becker introduced these notions in the 60s, the notion of taste-based discrimination in particular, which kind of is reflected in the more modern notions of fairness, then in a way he was kind of speaking to the civil rights movement, essentially telling them whatever the market produces that is by definition not discriminatory if it's profit maximizing. So in a way you might just go home because inequalities are fair as long as they are aligned with profit maximization. And only deviations from the market outcome of profit maximizing firms are unfair. And again, no matter how unequal they are. And so this kind of perspective then that's reflected in these fairness notions that are based on merit is that they have a number of normative limitations that I already mentioned. So they justify and perpetuate inequalities based on merit. Right? So they don't ask where does the difference in M come from. So say, if people go to different schools, then they might have different predicted productivity, say, and then fairness says that's perfectly fine then if their economic outcomes are unequal. And so this is reflected, for instance, in the tension if predictability is improved, either by better algorithms or based on more data, then generally that's going to increase inequality. It's going to make treatments more unequal since there is more variance in predicted M. But at the same time, it's almost mechanically improving fairness. So this is one example where there's a tension between fairness and equality. A second limitation of these definitions is that they tend to be narrowly bracketed. So they tend to focus just on inequality of W within the treated population, the algorithm, rather than inequality of welfare-relevant outcomes in the wider population. And so where it matters, for instance, is when we consider interventions that compensate pre-existing inequalities. For instance, something like affirmative action. But affirmative action is always a violation of fairness according to these definitions, like predictive parity. Affirmative action is bad for fairness, but if it's compensating pre-existing inequalities, then it is good for inequality. So again, another dimension where there's a tension between fairness and equality. And the third limitation is that these definitions of fairness, or at least most of them, tend to focus on categories or protected groups of people and tend to ignore within-group inequality. So, say you have the same number of men and women or black and white people in elite education institutions or corporate boards. These definitions would be happy no matter how unequal the outcomes are then between those who are in, say, elite education institutions and everyone else. This is, of course, also what's reflected in the intersectional criticisms of discrimination. And so based on this discussion of the limitations of such notions of fairness, what we propose is to instead, or at least as a complement, think more systematically about the causal impact inequality or welfare as an alternative. And so now I'm going to get a little bit more formal and technical here, and kind of drawing on the standard frameworks of causal inference, and in particular distributional decompositions as familiar in labor economics and public finance and economics. And so the simplest framework here would be the potential outcome framework, where if somebody is treated, so if their W is equal to 1, their outcome is equal to Y1. If they are untreated, then their outcome is equal to Y0. And now here, crucially, Y is an outcome that the individual cares about, right? So say like their income or whether or not they are in jail, which is different from M, which is what the decision maker cares about, which is essentially profits or productivity or recidivism. And so with this potential outcome notation, then for any treatment algorithm W, we can think of W as the probability of being treated conditional on X. So Wx is between 0 and 1. It's 1 if you're treated for sure, it's 0 if you're not treated. And then we can write the distribution of outcomes Y joined with X in this form, where we're integrating over the density of X, and then there's some mixture between the conditional density of Y0 and Y1 given X. And what we are interested in now is looking at statistics new of this outcome distribution. These might be measures of inequality, such as the variance or quantiles or quantile differences. Might also be between group inequality if we take into account A. And it might also be things like Gini coefficients or poverty rates or top 1% income shares. All kinds of measures of inequality could be considered here, or measures of social welfare. And here's kind of a classical result that's very useful in statistics and econometrics, which is that for sufficiently regular statistics nu, what we can do is locally approximate nu around some baseline distribution based on the expectation of the so-called influence function. So what this is really kind of a first-order approximation of functionals that map probability measures into the real line. So technically what the influence function is, it's the Riesz representative of the Fauché derivative of the functional nu. But for our purposes, what this is going to do is it allows us to consider any nonlinear measure of inequality nu, and locally it's going to be the same as the average of some influence function, which is going to allow us to leverage all kinds of standard off-the-shelf machine learning technology to predict conditional means. And in particular, the way that we can do that is based on this proposition. So what this proposition is saying is let's start with some baseline algorithm or baseline W star of allocating treatments, and let's locally perturb it. So let's take these baseline probabilities of getting treatment and let's perturb it in the direction dW of X by an amount epsilon. And that's our assignment probabilities W. And then what the proposition says is this local perturbation of the algorithm is going to have an effect on our three different objectives that we considered. It's going to have an effect on profits mu, it's going to have an effect on our measure of fairness pi, and it's going to have an effect on our measure of inequality nu. And moreover, this effect of this local perturbation can be expressed in this form as an expectation of the perturbation multiplied by these three influence functions, Lx, Px, and Nx. And so here is what these influence functions are. For the sake of time, I'm going to focus on L and N in my discussion now. So L is kind of maybe the most intuitive one. The impact on profits, if we increase the probability of Wx by some amount dW, is going to be just the conditional expectation of merit given X minus C. So if the expectation of M given X minus C is positive, then it's going to increase profits if we increase the treatment probability. Otherwise, it's negative. The expression Px for fairness is a little more complicated, so let me jump for now to Nx, which is the impact on inequality. And so this impact on inequality we can write as the conditional treatment effect on the inference function conditional on X. So in a way, this expression combines two things. First, there is a causal effect of the treatment W on the outcomes Y. So that would be Y1 minus Y0. And we could have the conditional average of that causal effect given X. That would be how much are the welfare relevant outcomes improved or worsened by increasing the probability of treatment given X. But then there's kind of a second aspect to it here, which is we don't just care about the average of outcomes, we care about the statistic mu, and therefore we don't evaluate the treatment effect on the outcomes Y, we evaluate the treatment effect on the inference function of Y. And so in particular, you can think about the slope of the inference function with respect to Y, that corresponds to what we can think of as a welfare weight. So the slope of the inference function measures how much does the statistic mu care about people with these values of X and these outcomes. So for instance, if you have an aversion to inequality, what the inference function would reflect is that it's putting a greater weight to improving the outcomes of those who are worse off, of say poor people, relative to improving the outcomes of those who are already better off, say rich people, and similar for other notions here. So this is kind of maybe slightly confusing technical way of expressing the impact of treatment probability changes on these different objectives. Why is this useful? So there are four reasons why we think this characterization is useful. The first one is kind of a conceptual one, which is elucidating the tension between the objectives that I was already talking about. So there's kind of this tension between fairness on the one hand and equality or welfare on the other hand. And so that's reflected here if there are values of X where the inference function Nx, say, is positive while Px is negative, then those would be values of X where increasing the probability of treatment is going to be good for welfare and equality and bad for fairness. So this allows us to characterize in a way where the tension is coming from in the space of features. Second, kind of more technically and more within the standard framework of fairness and machine learning, we can use these first order approximations in order to characterize the optimal solution to, say, profit maximization subject to fairness. And for that, you would, for instance, want to treat everybody whose Lx exceeds lambda times Px. So one is the inference function for profits, the other is the inference function for fairness. Third, like I said, I didn't have enough time today to talk in more detail about power, but what it allows us to do is think about the inverse problem, where rather than asking how do we maximize welfare by choice of treatment, we can say for a given actual choice of treatment probabilities, what are the implicit welfare weights? So what is the implicit power that's given to different people in terms of how much does their well-being count in social decision-making? And lastly, and that's maybe the most practically useful one, is this can be used for algorithmic auditing. So if you go to our paper, we discuss this in more detail, but essentially the idea would be to draw on this last characterization here using Nx, and essentially we can estimate the impact of any algorithm on inequality by first estimating Nx and then using this expression here to the top right for the epsilon mu. So how do you get Nx? Essentially, you would start with a baseline distribution, focus on some distributional statistic or some notion of welfare mu. Then you can estimate Nx using something like, for instance, a causal forest or some other machine learning method for the estimation of conditional average treatment effects. And then you can plug it in order to estimate the counterfactual causal impact of any algorithm on welfare and inequality. And we make the case that this is a useful complement to current practices of auditing that focus on fairness, and instead audit algorithms also for their causal impact on social inequality. And with that, I am out of time, and I thank you very much for your attention and hope to get to discuss more with some of you